Hi, today we're going over section 5.1, radical functions and radical expressions. In this video, we'll cover the idea of how to simplify a radical, and we'll do problem number 2 and number 3. In your notes, you see these 4 ways of how to simplify. So let's just talk about it and break that down. Number 1, the radicand has no factor raised to a power greater than or equal to the index. What does that mean? So if you look inside, if the inside number is bigger than the outside number, it's not simplified yet. Remember, if we had, for example, the square root of 100, this is the same as the square root of 10 squared. And so if I have 2 and this is the square root dividing by 2, I can pull those out. Same thing with letters. If I have x to the 4th and I want to divide it by 3, I could separate that. I could separate the cube root of x cubed, and then what would I have left? I'd have the cube root of x. Remember, when you multiply with 2 bases, you're adding the exponents. So 3 plus 1 would give you 4. So you kind of see there's a way to separate this, and the x cubed and the cube root, they undo each other. So if I was trying to simplify something like that, I would end up with x times the cube root of x. Let's look at number 2. Exponents in the radicand and the index of the radical have no common factors other than 1. So for example, if I wanted to write this as a fractional exponent, I would write x to the 2/4. Remember, inside is your numerator and outside your denominator. But 2/4 can be simplified to 1/2. So it's really x to the 1/2, and if I put that back to radical form, that would just be the square root of x. Okay, so there's another way that you can simplify the radical. What about the third way? The radicands have no fractions. For example, 1/9. We don't like a huge fraction under there. We want to clean that up. And like we previously discussed, you can split the radical to be root 1 divided by square root of 9. And then what is the square root of 1? 1. What is the square root of 9? 3. So this is really 1/3. And then the fourth one, no denominator contains a radical. So how do I do that? Remember, that's the process of rationalizing the denominator. Okay, so how do I get rid of the square root of 3? Well, if I multiply it by square root 3, I'm squaring a square root. That undoes each other. Awesome. But you can't just willy-nilly multiply by root 3, but you can always multiply by 1. Anything times 1 is itself. So you can manipulate the format by multiplying by 1, root 3 over root 3. I know what I need by looking at the denominator, and I need 2 of those. So make that a square root of 3, and then I put that in the numerator, and now I'm just multiplying by 1, so I'm set. So this would equal 1 times root 3, which is root 3, and root 3 times root 3, which is root 3 squared. The square and the square root undo each other, so you just get 3. And that's how you simplify by rationalizing the denominator. Let's try a couple of problems. Let's look at number 2. 25p to the 7th. Okay, there are 2 ideas here. First of all, you have a number like 25. You're trying to look for perfect squares. So anytime you see a number in front, you're asking yourself, what is the biggest perfect square that I can take out? 25 is a perfect square, so we love that. Next, I see p to the 7th. So when you're thinking about the letters, now you're thinking about grouping. What is divisible by the index? This is an index of 2. So what's divisible by 2? The biggest I can get. Well, 6 is divisible by 2. So I have p to the 7th. I split that into p to the 6th times p to the 1st, because 6 plus 1 is 7. Now I can take these 2 and clean them up and see what I have left. The square root of 25 is 5. What is the square root of p to the 6th? When you're dealing with numbers, you're thinking about 2 numbers that multiply to give you that value. 5 times 5. When you're dealing with exponents, you're just dividing. What is 6 divided by 2? 3. So that's p cubed. How does that work? Remember, we just talked about if I change that into an exponent, a fractional exponent instead of a radical, you would get p to the 6 divided by 2, 6 halves. That's just p cubed. Okay, so sometimes if you have radical form, you might switch it over to fractional exponent form, and so that can help you think about it. Otherwise, just think divide. When you're working with the exponents, just think divide. Divide it into two groups, something that's divisible by the index and whatever's left, and then divide 6 by the index. And there's your answer. Let's try B. All right, I think about 72. What is the biggest perfect square that I can take out of 72? And that would be 36. So I have the square root of 36, and what's left? The square root of 2. Then I consider my variables, x and y. Neither of them have an exponent that's greater than the index. So there's nothing I need to do, and they just stay under as x and y. So let's check out our answer. The square root of 36 is 6, so I'll have 6, and then all of these pieces stay under 2x and y. Okay. I like to think about this as you make two buckets, one where pieces can come out and one where you have to put things that stay underneath. And we'll talk about that later when we see some more examples. Okay, let's talk about C. Be careful. The index is 4. So you're trying to take the fourth root. I don't want perfect squares. I want something multiplied together 4 times to give me a number. Okay, so the fourth root of something. What about the fourth root of 16? And then what would be left? The fourth root of 2. Let's look at the letters. A to the 5th. How can I group that into groups that are divisible by 4? So a to the 4th, and remember it's the fourth root, and then times a to the 1st, and still the fourth root. All right, now let's see what we have. The fourth root of 16 is 2, and the fourth root of a to the 4th is a. And then what stays under the fourth root? You have a 2 left, and you have an a left. So the way I like to write this sometimes, now that you sort of get the idea, if you were to just see this problem, okay, the fourth root of 32, a to the 5th. And you get the concept now, so you write 2 fourth roots. I write a fourth root that can come out and a fourth root that has to stay in. What can come out? Well, 16 can come out and 2 will stay in. And how much can we take out of a to the 5th? We can take an a to the 4th, 4 can be divisible by 4, and there's just one a left. Then you go ahead and take the fourth root of 16a to the 4th to get 2a, and then you already know what's left and you don't have to think, oh no, what am I missing? It's already there. So that's a good way to organize it. Every time you see a problem trying to simplify a big radical, just make 2 radicals, remembering to use the correct index, and then what can I take out of there? Do I have a group of 4 some numbers that I can take out? Another way to think of 16 is to say, oh, this is 2 to the 4th. We could start back here at 32 and say, oh, that's 2 to the 5th. So 4 of them come out and 1 of them stays. There are many ways to think about it. I hope this is helping. Let's try problem number 3. The fourth root of 16. So I need 4 of the same number that will multiply to give me 16. We can think about this as 2 to the 4th, and then we say, oh, the fourth root and the fourth undo each other, and you just get 2. What about the sixth root of -1? If it's an even, anytime you're taking the even root of a negative, it's imaginary. So the sixth root of -1 would just be I. Now, if it were the fifth root of -1, then a negative times a negative times a negative times a negative times a negative, we can do that. So then you would get -1. Anytime it's odd, you can have a negative. If it's even, then it's imaginary. So let's look at the fifth root of -243. Since we have a -1 and then 243, we can think about what's the fifth root of -1. -1 multiplied by itself 5 times will give you a -1. So that piece is -1. And what times what times what times what times what will give you 243. And the answer is 3. So what's the answer to C? -3. Because it's an odd root, you can take that negative out. Let's look at D. What times what times what gives you 27? And that would be 3 again. 3 times 3 times 3 is 27. I hope this has helped you. We'll see you next time.